Target 6.6. Given the reactants of a single replacement reaction, I can use the activity series to predict whether the reaction will occur, write the net ionic equation, write oxidation reduction half reactions, identify the species that is reduced, oxidized, the reducing agent, and the oxidizing agent. First, we'll focus on using the activity series to predict whether a reaction will occur. The activity series is just a list of metals in order from most active to least active that's used in order to predict whether or not a reaction will occur. Just because you can put substances together and predict the products doesn't mean if you actually do it, anything will happen. We use the activity series to determine whether it will or not. So, here's how you do it. Here's just an excerpt from an activity series. If the single element is above the element in the compound, then the reaction will occur, because that means the single element is more active than the one in the compound. So you compare magnesium to the metal in the compound, which is potassium. Magnesium is here and potassium is here. Potassium is above magnesium, therefore more active. Therefore potassium will stay in the compound, so nothing will happen. You put no reaction. In this case, the reverse of that, potassium is above magnesium, more active, therefore potassium will end up in the compound. So go ahead and predict the products, cross over your charges. Potassium and chlorine both are 1, so KCl. Magnesium by itself is not diatomic, so you just leave it like that. Now, if the single element, the one by itself, is a nonmetal, you compare it to the nonmetal, which is the second element in the compound. If iodine is above bromine, the reaction will take place and iodine will kick bromine out and take bromine's place in the compound. Iodine here is shown below bromine, therefore it's less active, so bromine will stay in the compound, and this is a no reaction. The reverse of that, bromine and iodine. Bromine is above iodine, therefore bromine will take iodine's place. So you will have calcium bromide, and iodine will be by itself. It's diatomic, so you'd put a 2 there. Okay, oxidation reduction. Single replacement reactions are really oxidation reduction reactions. Oxidation is defined as losing electrons. Reduction is gaining electrons. A good way to remember that is just remember oil rig. Oxidation is losing, reduction is gaining. When something is oxidized, it loses negative charge, therefore the charge increases. When something is reduced, the charge goes down because it's gaining negative electrons. In this animation, magnesium is a solid metal, not charged. Dip it into a solution containing silver ions, and magnesium will give up its electrons to silver. Silver will then become a solid and precipitate out. The magnesium takes silver's place as an ion in solution. Watch it one more time. Magnesium gives up its electrons, therefore it's oxidized and becomes ions in solution. Silver, which were ions to begin with, gained electrons, precipitate out as a solid. Magnesium is oxidized, silver is reduced. Why is it called oxidation? Early chemists noticed that most compounds react with oxygen. Later they determined that when metals react with oxygen, they do so by losing electrons. They learned that oxygen's not the only element that metals will lose electrons to, but the name stuck. Reduction, when the charge goes down by gaining electrons, we say a species is reduced. Some practice. Here's some examples. Oxygen goes from a 0 charge to a -2 charge. The charge goes down, therefore it's reduced. Iron +3 to +2, charge goes down, reduction. Copper has a 0 charge and it goes up to 2, therefore it's oxidized. Aluminum +3 goes to a 0, reduced. Now, steps for writing single replacement reactions. First, check the activity series to make sure the reaction occurs. If it doesn't, just put no reaction and stop. Predict the products, add phases, and balance. Separate all aqueous into ions. Cross out ions that do not change phase. Write the net ionic equation. Write half reactions. Determine which is reduced and which is oxidized. We'll go through the steps. This wasn't supposed to be showing. You're given that zinc is put in a solution of sulfuric acid. First, check the activity series and make sure this reaction will occur. If you look at the activity series, you'll see that zinc is more reactive than hydrogen, so yes, this reaction will occur. Predict the products, zinc sulfate and hydrogen. Since hydrogen is diatomic, you put a 2 there. Now add phases. Zinc by itself is a solid. Acids are always AQ. This will be AQ, and hydrogen by itself is a gas. The next step, separate all the AQs into their ions. Leave the solids and the gases intact with no charge. Zinc solid. I left out balancing, but this equation is already balanced, so that works out. There are 2 hydrogens, and they separate into ions, so therefore +1 AQ. Only 1 sulfate. It has a -2 charge, and it's AQ. Zinc +2 AQ, and sulfate -2 AQ. Leave the gas intact with no charge. Next step is to cancel out everything that's AQ on both sides. Those are your spectator ions and not involved in the reaction. So zinc is solid on this side and AQ on that side. You can't cancel it. Hydrogen ions here, but it's a gas there, so you can't cancel it. Sulfate, AQ on both sides. Those are spectator ions. They remain in solution and never are involved in the reaction. Now what you're left with is your net ionic equation. Just rewrite it, include phases. There's your net ionic equation. Next step, write oxidation, reduction, half reactions. The way to do that is just copy down, separate the zinc and the hydrogen. Copy down the zinc exactly as it appears on this side. Copy down the zinc exactly as it appears on this side. Then you have to decide which side you need to add electrons to balance the charge. The charge is 0 on this side and +2 on that side. If you add negative electrons here, this will be negative and that will be positive. But if you add electrons on this side, you can bring that charge down to 0. So because it's a +2, you need to add 2 electrons. And now that's balanced. Do the same thing with your hydrogen. Copy it exactly as it is on this side. 2H plus AQ. And then exactly the way it is on this side, H2G. Decide which side you need to add electrons to in order to balance. This side is positive, that side is 0. So if you add 2 electrons to this side, it cancels out the 2 positives. Now it's balanced. Now, which one's oxidation and which one is reduction? 0 to +2, the charge goes up, therefore this is oxidation. +2 to 0, charge goes down, therefore this is reduced. Zinc is oxidized, hydrogen is reduced.